All right. Okay, so if, a couple of things, guys. Overcurrent protection devices, fuses, and circuit breakers. The code require all equipment and cables to be protected from overcurrent protection. When you go to a different industries, you're gonna see that they protect from all other than overcurrent protection device. They protect from over voltage, under voltage, frequency, over and under. So today, the only thing we're going to talk about, guys, is protecting from overcurrent protection. A couple of things I would like to go. NEC requirement, Article 240 for circuit breakers and fuses. We'll say a few things about this. You can only protect, for the most part, you can protect from overcurrent protection device using two devices, for the most part, either a circuit breaker or a fuse. There are different types of fuses and different types of circuit breakers. As we move into the commercial industrial, guys, we start studying the breakers in details and the fuses also in details as we move into it. There's also 5 possible conditions for the circuits. We're going to look at this. Various types of operation for fuses and circuit breakers. And you're going to spend the rest of, if you guys do overcurrent protection devices, which I've done a few of them, you're going to spend a lot of part of your career trying to understand different manufacturers' characteristics of their circuit breakers so you can specify the right circuit breaker for the right job and or the fuse. So single pole and two pole circuit breakers, this is very simple. We're doing residential, so we're talking about single pole circuit breaker, two pole circuit breaker, three pole circuit breakers with an approved handle. We're going to talk, guys, about the interrupting rating of the fuse or the circuit breaker and the available short circuit current, how to calculate that one. There are two concepts we invite Cutler Hammer to talk about, guys, next time. Very interesting concepts. And that concept is series rated panels, and fully rated panels. Series rated panels and fully rated panels. Now we're moving towards, have you guys ever heard of series rated panels? Electrical panels. Anybody ever heard the concept? What is a series rated panel? Anybody knows what a series rated panel is? How about a fully rated panel? Anybody ever heard of a fully rated panel, series rated panel? Okay, now that's what we're going to do. Selective coordination and non-selective coordination. Anybody knows what a selective coordination is? We talked about this one before. What's a selective coordination?
Only the breaker affected by the overload.
Thank you. The breaker that's affected by the short circuit or the overload will trip before the mains trip. That's a selective coordination. If you don't know it, I guarantee you as we move forward, guys, you're going to be doing coordination. You're going to be using a software to do all these coordination and set up for all these relays and circuit breakers. So it's coming. So these are the few concepts in this chapter that I thought to prep you to what's coming in the commercial industrial. Overcurrent protection device, Article 240, as you know, guys, cover it. For residential only, we will be talking about overcurrent protection device in the commercial and industrial. So this is just FYI, this is going to be a focus on residential. If you have a service, which you must, if you have a branch circuit, which you must, and if you have a feeder, which you must, these must be protected by a fuse or a circuit breaker, right? So we talked about, guys, the 3 very important circuits in any electrical system. We said the service conductors, the feeder conductors, and the branch circuit conductors must be protected at the point where they receive the power, the juice. At the point that they receive the juice, they must be protected, with some exceptions, protected by an overcurrent protection device that limit 2 things. Limit the amount of current that the conductor can carry to its capability under normal condition. That's number 1. Number 2, limit the amount of short circuit energy that the conductor can handle to its capability before it starts smoking. So these are what we're going to be talking about: the fuse, the protecting branch circuits and feeders and services using breakers and circuit breakers, breakers and fuses. Okay, so if I have just a quick conductor, guys, just a quick conductor, quick example. Let's take here's a 20 amp circuit. Chris, what do you think a 20 amp circuit conductor size? 12 goes with it, right? Okay. So what we're saying here is that current can go up to under normal condition, can go up to non-continuous, up to 20 amp in this conductor, and this conductor will continue to operate fully functioning, right? Are you with me? Up to 20 amp circuit. Overload, we're fine. Non-continuous, up to 20 amp. Now take this. If I have a short circuit here, here's my equipment here. This is my garbage disposal. Now, Nick, because he's sometimes troublemaker, he went and shorted. He made a short circuit, grabbed the hot, and tie it to the frame of a garbage disposal, intentionally or unintentionally. So the amount of current, now we have a short circuit. The amount of current that's going to go right in here, it's going to be, I'm going to say 5,000 amp. It's going to keep going all the way to the short, right? You have a 5,000 amp, you shorted, line to ground, you have a short circuit or a ground fault, right? 5,000 amp, yeah. This circuit breaker also has to be rated for 10,000 amp. Take this. The conductor must be able to handle the 20 amp forever going through it. That's the load. The 20 amp is a load. The same thing, the conductor must be able to handle the 5,000 amp if there is a short circuit in this piece of equipment, not forever this time. Not forever. For a predetermined amount of time. Usually 3 cycles. 3 cycles is 3/60. That will make it 1/20th of a second. 1/20th of the second, that conductor must not burn, smoke, heat, until, what happened in that 3 cycles? The circuit breaker will wake up and decide, oh, we have a problem here, and it opens within 3 cycles. Any question, guys, about this? Any question? So we have an overcome protection device. The most important thing, Oladipo, is this. We have an overcome protection device that protects from overload. This is this from load and short circuit or ground fault. So here's your load, and this value is for what? For short circuit and ground fault, for faults. So every circuit breaker has 2 values. One to protect you from short circuit and ground faults, the other value to protect you from overload. Conductors have to have 2 values. One, continuously carrying the amount of current, continuously, right? To carry the amount of current under normal conditions. And the other one is, if upon the existence of a ground fault or short circuit, would this conductor be able to continue intact without burning? Any question, guys, about this? That's what the circuit breaker is supposed to do, to protect you from mainly 2 conditions, faults and overloads. Any questions? Nick, does it make sense? And you guys have been doing this with me all the time. These are a couple of articles, guys, that we're going to be hitting on as we go through, that talks about overcome protection devices and requirements and so forth. Especially the articles that talk about service conductors and sizing service conductors. We will be hitting these as we go through the year. So, and I'm going to move all the way to the following. Okay, if you have an electrical circuit, if you guys have an electrical circuit like this, there are 5 conditions of this circuit. 3-phase or single phase, it doesn't matter. DC or AC. AC, DC, 3-phase, single phase, what else? Any type of electrical circuit. There are these 5 conditions. Condition number 1, normal. That's what we love, what we wanted to do. Take this one, Nick, my friend. I have a power source. Here's my power source coming from right here, from Excel Energy. And my power source, this is 7200 volt transformer sitting on the pole. Coming to your house, you have a 15 amp fuse with circuit breaker, and your load is a 24 ohm, your garbage disposal. So you have, look at this one. You have this amount of current going through your conductors. This amount of current going through your conductors. Your conductors here, is just sizing at number 14. So am I okay now? I have a 9 amps going through number 14 conductor protected by 15 amps. Am I okay? Right? So the current is going in both directions in this case. So I have a 15 amp fuse protecting number 14 to feed the load, and everything is up and running. Is this okay? Is this okay? So that's a normal condition. Normal condition is, what's a normal condition? Normal condition is you cannot, if you tell me, if you guys go to how much current number 14 can carry, with restrictions from the code, 15 amps. So have I exceeded the 15 amps full load on that? No, so I'm good. How much current continuously can a 15 amp fuse carry or circuit breakers? 80% of 15. 12. 12 amps continuously. Have I exceeded the 12 amps that continuously out of this fuse or circuit breaker? No. So that's a normal condition. You can run this forever. You can run like this forever. So here's how they came up with the current, guys, from Ohm's law that you did with Gary and before Chad, and with all our electrical instructors. You take the ohm to find the current, Ohm's law. You take the voltage, the mother voltage, divided by the impedance of the load, which is substantially more than the impedance of the conductor. Substantially more. So if you guys look at 24, here's my 24, substantially more. Then you add to it the impedance of the conductor. To add to it the impedance of the conductor. My conductor conductors is 0.015. Remember how we found the resistance of the conductor based on the length and the size from table 8, chapter 9? That's what they got this. So here's why do you guys have two of them? Right here and right here, because we have two conductors going both directions. And also they have an impedance, guys, for the source. They added the very small impedance the source provided. I want you to see, look at the 24 compared to all other impedances. By far, the impedance of the load is substantially more than the impedance of the source, as well as the impedance of conductor. I don't know, Chris, if Gary told you guys, when the impedance of the source becomes equal to the impedance of the load, you have no current going through that conductor, nothing. Everything, all the current will be sucked and being eaten by the source. So that 0.001, if it becomes 24, that load is going to see nothing. So anyway, if you do all your math, you're going to find 9.87 for all practical reasons. For all practical reasons, guys. That's why we assume it's always E over R, and it's always 240 over 24, and that equals 10 amps. This is what we do 99% of the time. We assume the impedance of the conductors are negligible, right? And if you can see 10 amps, I can easily, 9.987 amps, I can easily make it 10 amps. Any question about this? This is very important, guys, to understand the 5 conditions of a circuit. Any question about this? So, Phil, my friend, 99% of the time, if you take the 24 divided by 2, the 24 divided by 240 divided by 24, you get 10 amps. That's great. What did we do then? We ignored the impedance of the source and the impedance of the conductors, which is acceptable because it's the load impedance is substantially more than the impedance of the conductors and the source. So for all practical reasons, we can assume the conductor impedance and the source impedance is 0 when we calculate the current. Any question, guys, about the normal condition of the circuit? Now let's go back to another condition. So here's a normal condition. Another condition is the overload. Now Chris, my friend, decided to go buy another garbage disposal and tie it to the same circuit. That's what we're doing. That's what overload is. You decided to go buy another garbage disposal and tie it to the system. Look what happened then. Then if you guys remember, if you put two loads in parallel, what happened to the impedance, overall impedance of the two loads? It's cut by half if it's the same. So look at the R, that 24R became 12R, and I hope for Pete's sake, you guys know how to do that. When you have two loads, if I have a city of Bloomington and clone the city of Bloomington here and tie the two city of Bloomington to the grid, the overall impedance will go down because that's the beauty of the parallel circuit. Every time you add a load in parallel, the overall impedance of the system, what happened? It goes down. Okay, so that's 12. Okay, look at this. Everybody knows why 12, because I added two resistors in parallel. Now do the same math. Let's do a simple math. The simple math is I equal 240 divided by 12, and that will give me in this 20 amps. 20 amps. That's a simple math, ignoring the impedance of the cables and the conductors, which is what we do all the time. Ignore it because it's not substantial. And you agree with me, 19.948 or 46 is really close to 20 amps. Okay? What happened to now? Take this, Chris. What happened to number 14 conductor? It's supposed to be carrying limited to 15 amps. This is overloaded. Overloaded. Are you guys with me? How about what happened to the fuse? The fuse is also overloaded. This is what's called the overload condition. You double the load, triple it, increase it by 50% or 100% or 150%. That's an overload condition. Still, guys, the same impedance of the resistors and it's still there. That's an overload condition. What happened in an overload condition? This fuse will sit there in this situation probably for an hour, half an hour and a half, and it will open. So look at the amount of time that it takes to open. If you double it, probably you're talking about in hours from I don't know, 0.4 of an hour all the way, say, to 1 hour. It might take 0.4 of an hour, 20 minutes or so, all the way to an hour, and it opens. Thank you. It's a function of heat. Because the overload, what happens with the fuse, guys, the fuse element is going to be overheating, and when it reaches a point, it will reach a point where we'll melt the fuse element right here. There's a fuse element right in here that need to be heated. So it takes time to heat this element. And that time is usually in minutes. In minutes all the way to an hour. It could take an hour for this one to trip. Okay? In minutes. Not in seconds, not in cycles, in minutes. Any question, guys, about overload? So it might take 10 minutes for this one to trip. Or 20 minutes, depending on the type of the circuit breaker, the setting of the circuit breakers, and so forth. And by the way, Nick, if you tell me, Chad, can you give me an answer exactly 20 minutes or 30 minutes? I can. If I have the current characteristic curve of this fuse, I can tell you if you load it with this amount of amps, it will trip in 20 minutes. Obviously, that's what we predict an equipment might. So there's a tolerance plus or minus that 10%, 20 minutes, plus or minus, say, 10. There's a tolerance, as you know, Chris, for equipment. Any question, guys, about the overloaded condition? That's what you don't want your system to be. You do not want your system to be overloaded. Ashley, my friend, Zach, you guys have any question about the overloaded? I can't emphasize, because you hear these terms all the time, overloaded, guys. That's what overloading is. Cool? So we go to next, the same circuit. Let's look at the second one. Now, the troublemaker, my friend Nick, the one who just shorted the garbage disposal, is doing it again. So that's what he did. He went right here to the hot and grabbed it to the other hot and tied a jumper. He jumped them together. So right the wire right across and jump them. You know, that's an excuse for horse whipping, like Chris, my friend, always say. It's a good reason for horse whipping. Okay, look what happened though. But the beauty is, look what happened. Now, what happened to that 20? I want you guys to look at this one. What happened to the 24? The 24, the impedance of the 24 is gone out of the equation. It's gone out of the equation. So look what happened. You take the in parallel, the impedance of this wire is almost zero. So you take a 0 with 24. Look at that, 0 times 20. You know how to put a wire with a zero impedance, almost zero impedance, across a load. You are looking at almost zero impedance. So the current is not going to see any resistance as it goes through. Almost zero. Obviously, it's not zero. Otherwise, it will be infinite amount of current going through it. So what happened is, you guys remember the 24 that used to be here? That's gone. So now, the only impedance is the impedance of the two conductors and the source. Thanks God there is some impedance. Otherwise, you will burn the equipment completely. You have to have some impedance. So look what happened here. This becomes very interesting. We take the 24. The only impedance is the impedance of the cables and the source. Mostly the cables. So divided by point, which is tiny little. So look at that current that's going to grow. Math, just divided by a very small impedance. Look what the amp, 7.7K. This is a 7.7K kiloamp. 7.7 kiloamp. That's a short circuit, right? That's a short circuit. Now look what happened. This conductor, do you guys remember what we said? This number 14 conductor? Number 14 conductor can carry 15 amps, and at the same time, it's rated to handle the short circuit up to I'm going to say 15,000 amp for 3 cycles. Okay, look what happened now. I have, how much current do I have here? I have 7.7 7.7 kiloamp short circuit going through it. The fuse is rated, my fuse is rated for 10,000 amps. Okay, so, and I have a short circuit 7.7. Now look, Nick, if you see, have I exceeded the rating of the fuse with the short circuit 7.7? Is it higher than what the fuse is rated for? No. Okay, would the fuse explode then? Now what happens if this was higher? Your fuse will explode. Your circuit breaker will, if it's circuit breaker, the contacts of circuit breaker will arc enough that they will be welded together and act as a conductor. It can't open. So, but the circuit breaker is rated, this guy is rated for 10K. I picked it up 10K. The conductor can handle up to 15. This can handle up to 10K. And I have 7.7K. Then what's going to happen to the fuse? It's going to open. But it's going to open for how long will it take the fuse to open normally? We're going to say in a range of 3 cycles. What is the 3 cycle? 3 cycle, you take the 3 divided by 60 in the US. That'll give you 1/20 of a second. Can anybody witness an event 1/20th of a second? That's fast. Now, if it doesn't open that fast, or if it doesn't open fast, here's what's going to happen. The insulation here, this starts heating up, heating up, heating up, heating up, heating up. At a certain point, the conductor, the insulation will melt, and if it continues to heat up, the copper will evaporate too. It will melt the copper. And it becomes a fuse. The conductor becomes a fuse. Any question, guys, about the short circuit? I can't emphasize the ability to understand it, guys, because that's how we're going to be doing as we go to commercial. We're going to size equipment based on the short circuit. Any question about the short circuit condition and why it's dangerous and why we have the conductor have to be rated to handle as well as the fuse have to be rated to handle. Now, Oladipo, let me get you this scenario. Suppose that this current was, let's say, 20,000 amp. Just when because of the current, came up with 20,000 amp. Number one, what's going to happen to your circuit conductor here? Smoke. There's still smoke, right? Smoke. What's going to happen to this guy? Explode, or weld, not open. If the short circuit, available short circuit is this amount. It's not rated to handle that. It's not rated to handle that. So your job, Zach, is to specify a fuse and a conductor that can handle the short circuit. How would I know, Chad? That's why you guys are going to be doing with us short circuit analysis. You hear the word short circuit analysis, over current protection coordination. We're going to be doing it next quarter and the quarter after. So you can pick a fuse that can protect your conductor from smoking, and your equipment, also the equipment, from smoking. Any question, guys, about the short circuit condition? Short circuit condition? That doesn't make sense. So normal condition, then overload, bad, but this is bad. This is worse. Okay, now short circuit, guys, is when you take a phase to a phase. That's what a short circuit is. What's the difference between short circuit and ground fault? Short circuit is you take a phase to a phase, a hot to a hot. That's the short circuit. A short, here's two hots and here's a ground. Okay, take phase to phase or hot to hot, that's short circuit. If you take phase to ground or phase to neutral, that's a ground fault. That's it. It's still bad. It's still a fault. So the fault can be short phase to phase, or can be phase to neutral, or phase to ground. If it's, what's the worst? What's the worst? The worst, guys, is usually phase to phase. If you have phase to phase, three phase, phase to phase to phase, three phase together, bolt them together, that's the worst scenario. Under certain circumstances with generator, the ground fault can exceed the three phase. I don't want you to think of it, because we always limit the available short circuit to the three-phase condition, which is the worst scenario. So if anybody asks you what is the worst scenario for a three-phase short circuit, three-phase. When you take phase A, phase B, phase C, now the troublemakers, Oladipo, not Nick, grab phase A and phase B and put them in a wire knot and tie them together and turn the switch on. That's the worst scenario. Now we don't have, if it's single phase, like this system, the worst scenario is take hot 1 and hot 2, tie them together with a wire knot, and turn the switch on. Did you? Okay, short circuit. Let's look at the ground fault. So what's the ground fault, guys? The ground fault is a short circuit, exactly a short circuit. So I want to do it right here. If I have a ground fault, suppose that I have a green conductor coming from here. Here's my ground, and here's my conductor coming all the way to tie to the equipment, right? And then the troublesome trucks, my troublesome friend Dustin this time went and grabbed the hot and tied it to the ground conductor or the neutral conductor. Any grounded conductor could be a equipment grounded conductor or grounded conductor, the neutral. Tie them together. That's your ground fault. What's the difference? The ground fault, this is not as high as the three-phase. This is not as high as the three-phase. It's going to be less than the three-phase. The same thing, you're going to get, so if you have a ground fault like this, the current that you might encounter here could be 4,000 amp. Now I'm going to look at Nick and tell you, Nick, if it's a 4,000 amp ground fault and a 7.7 short circuit, can this conductor under these circumstances, 15K and 10K, handle the 4K? Yeah, if they can handle 7.7K, they can handle 4K. That's what the ground fault is, a fault that less damaging than the short circuit. How do you get a ground fault? You take a phase to a conduit, grounded. A phase to the neutral, grounded. Anything that's grounded, get you a ground fault. Okay? So the reason why, if you size for the short circuit, then are you covered by the ground fault? 95% of the time you are. So that's why we worry too much about this circuit, not this circuit. You can do the same impedance, guys, because if you do a ground fault, it's, you know, it could be, the impedance could be higher in a ground fault than on a short circuit. Any question, my friends? So ground fault, what's the difference between phase? Lower amps. As you guys can see, we got 4K here versus we got 7.7. How did you get the 4K? Not rocket science. You take the 24 volt, take one impedance here, the other impedance, the impedance of the grounded conductor too. We're going to take it, and the impedance of the connection here, that connection that has an impedance. It might not be touching. You know, there is a gap, a little gap, or something start arcing. So they all take this into consideration. Almost always guaranteed you're going to get lower than that. Okay. The last one. So any question, guys, about the normal circuit, the overload, the short circuit, and the ground? Short and ground are almost tied together. The last one is open circuit. Open circuit is as it's bad, but not as bad as a short circuit. Open circuit system doesn't work, though could be damaging. So open circuit. Now who's the troublesome? Jackson, my friend, went to a wire nut sitting like this. That's supposed to tie the circuit, the motor lead hot to the lead coming from the service and tied with a wire nut. He unscrewed that wire nut, right? And you open this circuit. So what's going to happen, guys, to a motor like this if you open the conductor? Nothing. This machine is off. This machine is off. This is in single-phase system. In single-phase system. In a three-phase system, open circuit is bad news. So if it's a single-phase system like this, what's going to happen to the 24 volt? Nothing. Okay, but take this. Here's my neutral. I brought my neutral here. And here's my neutral up here. And I have a load. This load now needs a neutral. And I brought another load right here, another 24. Okay? Oh, they're sharing a neutral, right? Take this. What happened if you open the neutral? That's an open circuit. What happened if you open the neutral and open circuit? You burn the equipment. So open circuit could be completely damaging, right? You open a neutral, that's an open circuit. You open part of the circuit, that's open circuit. You burn the equipment. If you open a circuit like the example that we have, one hot and the circuit is 240, nothing will happen. Take this. If you have a three-phase motor, 1, 2, 3, and you have your circuit fuse here protecting a three-phase. We'll talk about this one, guys. And everything is tied. And oops, I have a fuse open here. I had an open fuse here. So actually, what happened here? I have a fuse open. This is a 50 horsepower motor, three-phase, 480. Is this an open circuit? I have a phase open. That's an open circuit. But I have two more phases still up and running though. If this motor is running, guys, you know what happened? The motor starts sucking more current out of the two other phases, and the other two phases will be overloading unless you have an overload sized right here. Unless you have a nice overload sized here. This is my overload. This will be carrying 100 and close to 130%. This will also carry 130% or so. So this will be zero, right? 0 amp going through. It's open. So you're overloading the other two phases. Two things happen. If you allow this overloading to continue, you're going to burn your equipment. Overload because of open circuit. If smart enough, we put overloads, guys. You've been sizing overloads. So this overload will see that there is a 30% increase on this phase, and within a minute or so, trips and open and save your motor from burning. Any question, guys, about the open circuit? So open circuit is things doesn't work if it's single phase. If it's three phase, things could burn too. Bad news. Bad news. Any question about these 5 conditions? Open circuit, short circuit, ground fault, normal, and overload. Okay, look how they do it. I don't know if you saw that one, how they calculate it. If you take 24 divided by, if you have an open circuit, what's the impedance of an open circuit? A short circuit impedance is what? 0. What's the impedance of an open circuit? Infinity. Unlimited, huge number. So that's why everybody knows that symbol of infinity. A huge number. Divide anything by infinity. I don't know if you did that in school, Chris. When you divide things by infinity, you can approach the infinity. It will give you a 0. If you divide things by 0, as you approach the 0 from right or left, okay, we're not going to go to the math. You get closer to the infinity bar. Okay, so that's any question, guys, about the three or the 5 conditions of fuses and 5 conditions of circuits. This is to prep you to understand why do we use fuses. Okay, now the NEC code book, guys, talk about fuses in 240. And for fuses, we talked about the fuses. You have plug fuses. You guys have seen that one that comes in the garage door opener, that plug fuses. You plug it in, Edison type base plug fuses. These are come up not exceeding 124 from the code, and you have to put them on a grounded system. Grounded neutral, and you can't exceed 150, which is limit you. There's 2 limitations on these. Limitation number 1 is the amp. Limitation number 2 is the voltage. So these are 120 at 30 amp max. If you have these plug-in, guys, that we use them, they're limited to 120 volt, no higher, 120 volt, as well as 30 amp max. 30 amp max. Any question about this? That's what you're not going to be using in commercial industrial, though. This is not what your commercial industrial. Plug-in fuses. Okay, plug-in fuses shall be, I don't know how many of you guys, probably, Chris, you have done it many times. What happened in the fuse boxes in the past is if the fuse blows and you don't have this size of fuse. You use a penny, you stick the penny under, and you tie the fuse over it. So you basically defeated the purpose of a fuse, right? Or what happened in the past, we use a 15 amp fuse, and you don't have a 15 amp, you have a 20 amp fuse, and they fit. So you put a 20 amp fuse. So now you are having a number 14 conductor carrying, say, 20 amp or 24 amps or so. So you're basically overloading your conductors. Because of all of this, the smarter than Chad start using the S fuses, the type S, where they have that little piece that you stick it inside the plug-in fuse, and it will limit you to certain sizes. So if it's 15 amp, it'll limit you up to 15 amp, 20 amp up to 20 amp, and 30 amp up to 30 amp. Here's the ranges that we do. You have range 0 to 15, and 16 to 20, and 20 to 30. So if you put that plug in, you cannot put more than, you plug it at 15, then you can't put a 20. If you plug it at 20, you can't put a 30 amp. This is, guys, for tampering with the fuses. I don't know if you've seen the fuses. You worked in our lab. So, if you know, unless you have this little S-type fuses, then you can't tamper with the fuses. They don't want you to tamper with the fuses. Any question? What we suggest here, this is an excellent for protecting motors. We use them in our motors. We're talking about single phase residential. They use them sometimes, guys, with the garage door opener. They have in the garage door opener box with a fuse, and they use it as a supplemental overcurrent protection device to the garage door opener. Commonly used. So you put a 10 amp fuse to protect the motor. Any question about the fuses? This type of fuses anyway. This type of fuses, the plug-in fuses. Okay, time current. Every fuse have a time current, guys. That's a time current, as well as every circuit breaker. Open under different conditions. Let me draw a time current for you guys. Here's the amp here. Here's the circuit, the time. So a fuse, we'll look at a fuse. Here's a fuse curve. And I don't want to go there because I will get you guys there. This is a 15 amp fuse. And this can handle up to this point is 10,000 amp. Can you guys see that? So the fuse can protect you from 15 amp all the way to 10,000 amp, overload, short circuit. So that range here, anything in this range is called the protective. Anything in this range is protected. You're protected by the fuse. So I can get up to 15 amp continuously. The difference here, this is the ground, this size here. This size is false. False. So this side is false. This is load. So if you are in this range, the load range, you're protected from protected. And if you are in the short circuit or the ground fault range, you're protected up to where? Up to this point. Now take this. If you're in this range here, you're doomed. That's where you're doomed, right? That's where smoke starts coming out, yeah? So say if you have a ground fault up to, I'm going to say this is 30 cycle. If you have a ground fault, say 7 kilo amp, it takes 30 cycles to clear it. And I'm just throwing these numbers in cycles. If the short circuit is lower, right here, it will take 3 cycles. This is what they call it time current characteristic curve. You're going to study this in details as we move on. So I'm going to stop right there. But that's what they're talking about, the time current, guys, time current characteristic curve. Time current characteristic curve, which is that curve right in here. That have a relationship. The higher the amp, the faster that baby will trip. Okay, fuses. You can get fuses, guys, dual non-time delay fuse, single non-time delay fuse. You can have a dual element time delay fuse and locked spring time delay fuse. All these guys, time delay or non-time delay to get you for overload and starting a motor. So if you have a non-time delay fuse and you put it on a motor, it could see, if it's not sized right, it could see the inrush of a motor as a short circuit, right? So you allow that curve, give the curve enough room. So if you move this curve up, and I don't want to even go, move it up to there, up back, it allows the motor to start. That's why a time delay fuse. Inject some delay before the fuse will open. If you guys get this one now, as we move through into the fuses and the coordination, that will help you a lot. Any question? The most important thing is time delay and non-time delay fuse. We use them in motors. If you remember, Chris, if it's non-time delay fuse, 300%. If it's time delay fuse, 1.75. Because we can have a smaller fuse because it allows the motor to start. Okay, questions? Any questions? Any questions?
What's the loaded length system?
It has some time delay in it, I think. So that's time delay fuse and loaded link. I think it has, there's so many types of fuses, guys. I think it has some type of delay in it. That's why they have the loaded link in it. I have to look it up. Okay, so cartridge fuse is available with 3 basic types of time current characteristics. A couple of, and I promise you, Chris will talk in the fuses more as we go deeper, guys. This is just because that's all what we do. When we talk about most common fuses, dual type, here you go. This is the most common ones, dual element cartridge fuses. These are the look like a knife cartridge fuses. You can get them rated to 250, 600 volts, and you can get them up to 600 amps, and they go even up to 6,000 amps. Cartridge fuses, guys, different type. And again, I don't want to open this can of worm. And different types that they use them. Some of them fuses can be non-time delay fuse, time delay fuse. They can be current limiting fuses. They can be the most important thing, guys, time delay fuse, dual element time delay fuse, non-time delay fuse, and current limiting fuse. We'll talk about it in a second. I'm not going to talk about the types because we hit these as we go through a commercial. Different types for different applications. The voltages, 250, 600, you can go even higher than that one, up to 6,000 amp. Up to 6,000 amp. Okay, circuit breakers, my friend. Circuit breakers is the most common ones that we use in residential. The most important circuit breaker that you guys use is thermal magnetic circuit breaker. Very simple. As the current goes through, two pieces of material are heated. If it reaches a point where it heats far enough, it will deflect and open the circuit. It will deflect, push down on a contact and open the circuit. So it's a heat function. It has a heat function. The thermal part is overload. The magnetic part is short circuit. Very important, guys. This device is made out of two components, the circuit breakers. Unlike the fuses, which dual element time delay fuses have two components. Unlike the non-time delay fuses, which has one element, if it's overload, it takes time to heat it and break it. If it's short circuit, it heats faster and open. That's a fuse. Circuit breaker have two components. One is thermal, so two pieces of metal. You go right this similar material, your current goes through it and they expand at different rates. So if you overload the circuit breaker at one time, these will expand and move away from each other to push a contacts to open the circuit breakers. That's the thermal part. The short circuit, guys, has some type of a coil. If you put current inside this coil, create a force, a magnetic force that immediately pushes contacts and open because of magnetic force. That's where the magnetic part came to be. Okay, we will talk about electronic circuit breakers later, so don't even open that can of worm. Electronic circuit breakers, guys. I want to remind you that unless circuit breakers are rated for 100% on overcapacity, only if it's listed for 100%. So, for example, if I have a circuit breaker that's 100 amp, most likely, how much current can I pull out of this 100 amp? 80%, 80 amps. So circuit breakers, guys, unless they're listed, which they make them, and it makes more sense to start using 100% rated circuit breakers if you're dealing with 600 amp to 1,000 amp or higher. That's where we start using. If you have 600 amp or all the way to between range 600 to 1,000 or higher, that's when you start making more sense to use 100% rated circuit breaker. So I have a 4,000 amp circuit breaker that will carry continuously forever a 4,000 amp. That's what that means. Okay, for most of the time, the application right now that we do, guys, is most of them are 80% rated, meaning you cannot pull continuously 3 hours or more than 80% of these circuit breakers. That's why we size them, the brand circuit that we were doing, we said limited to 16 amps and 12 amps and 15 and 20 amp circuits. Okay, very important because of the temperature, obviously, because the way they work. You can have circuit breaker single pole for 120 or two pole for 240. You can tie two pole circuit breakers and put them on a two pole load, right? But they have to be tied in an approved manner. We all know, guys, if I have a circuit breaker, I know I'm reviewing things that you guys know. I have my garbage disposal here and my dishwasher garbage disposal, and then I brought my neutral here, tied it, and I went all the way to, this is my neutral. This is hot 1, hot 2, right? In a case like this at 20 amp, you have to be tied together. You can use two single pole circuit breaker tied with an approved handle, or you can use a two-pole circuit breaker from the get-go. What's a two-pole circuit breaker, guys? It's molded with contacts with one handle that can turn them on and off the two poles.
One cheaper than the other?
Yes, I think the two-pole tied, that's what we use it more often than the tied single pole tied together. Any question, guys, about this? You can use this also on a 240 load as long as it's up to no more than 240 with a grounded conductor. Split phase circuits. Handle ties have to be approved and permit breakers to switch them on and off. Tested and listed. That's where the handle have to be tested and listed. Okay. Any question, guys, about the circuit breaker? Quick overview of circuit breakers. Any question? The code actually says if you have a fuse and the fuse interrupting rating is more than 10,000 amp, you don't have to label it. So if it's 10,000 or less, you don't have to label it. More than 10,000, you have to label it. If it's a fuse, if it's circuit breaker, if it's 5,000 or less, you don't have to label it. If it's more than 10,000, you have to label it. What am I talking about labeling, guys? You have a circuit breaker like this, 100 amp. That's not enough to say 100 amp. What's the interrupting rating of this 100 amp? Well, the interrupting rating, if I just put it this means it's 5,000 amp or less, if I don't label it. Now, hopefully that wouldn't happen. So I need to go there and put 22.5 kiloamp. So this circuit breaker now can handle up to 22.5 thousand amps or 22.5 kiloamps, a short circuit, ground fault, and so forth. Any question, guys, about circuit breakers, thermal? We're not going to talk about the electronic circuit breakers yet. We will open this can of worms as we move to the commercial industrial. Thermomagnetic circuit breakers, you're looking at them right in here. That's what they call the thermomagnetic circuit breakers. Why they are thermal? Because they work on heat. Why are they magnetic? Because there's a component that works in a short circuit, in a magnetic force, to open the circuit breaker fast. So, any question, guys, about the circuit breakers? Circuit breakers, you can get them from 15 amps all the way to 6,000 amps. The most common circuit breakers that we use in the industry, guys, are rated from 15 amps all the way to 4,000 amps. I've never seen a circuit breaker more than 4,000 amps. They can be thermomagnetic circuit breakers. 90% of the smaller circuit breakers are thermomagnetic, or they can be electronic circuit breakers, which becomes like your laptop, has a brain, complete brain with it, functioning circuit breaker. They can be molded like these ones that you're looking at, or you're going to see later on when we go 2,000 amp, they can be a foot by a foot by a foot draw out circuit breaker. Imagine a foot by a foot by a foot, 3-dimension, big block with a brain in it, electronic brain in it, that you can draw, pull in, pull out, draw, put it on the table and fix it. We'll talk about these as we go through. Any question, guys? Any question? Okay, I'm going to give you a quick break, and then I really want to hit the fully rated, series rated panels. So. This concept, fully rated, as you said, guys, some of you have never heard of it. Fully rated and series rated. The reason why they have a fully rated panels and series, we just started, guys. Thank you. The reason for we have fully rated and series rated is only one reason, right here. Less cost. That's the only reason why we use fully rated, series rated equipment versus fully rated equipment. We will talk about them in details, guys, when we invite Kyler Hammer rep. When he comes here, he shows you a lot of equipment. So that's the only reason. Otherwise, everything will be. So what's the default? The default should be right here. This is your default. The default is fully rated equipment. That's your default. Series is exception. Series rated equipment is exception. So what the heck do they mean? Let's go directly into a panel. Here's a fuse panel, guys. And if you have, look at that. This is related to the short circuit. if you have a short circuit, look at the short circuit right in here. If I made a short circuit right here at the terminals of the transformers, three phase, I'm going to find this amount. This is at 20.8 thousand amp will be rushing right through my switch gear if I made a short circuit right at the transformer terminal. Okay, so if I made a short circuit right in this area, I'm also expected to get something like this, 20.8 thousand. So Chris, my friend, if you are, here's what's the available short circuit. What do you think this fuse should be rated for? 20.8 or higher? Let's use the 25. So this fuse is rated for 25,000 amp. How about here? If I have a short circuit right in this area here, I'm also close to 20.8 thousand amp. So what do you think all these fuses here has to be rated for? They have to be, all these fuses have to be rated for a 25,000 amp. This is, my friends, is called fully rated system. Fully rated system. So the main and every circuit breaker or fuse in the same panel will be rated for the same short circuit. For example, you can see the main is rated for 25, as well as the subs. All the subs are rated for 25. That's fully rated system. Fully rated system. What's wrong with this? This is the best. What's wrong with this? This is expensive. To buy a 25 circuit breaker versus a 10,000, a 25,000 interrupting rating circuit breaker versus a 10, you could have increased your price of a circuit breaker because they manufacture it differently and it costs them more to do it. You could increase it by 50% or 25 to 50%. Any question, guys, about short circuit versus fully rated system? So what is a fully rated system? You walk into you look at a panel like this, guys, and if this panel has a main right here, the main will be 25, and each one of these circuit breakers will be 25, 25, 25, 25, right in here. That's fully rated system. Where would you use a fully rated system? Fully rated systems start making a lot of sense, guys, if you're looking at 600 amps or higher. 600 amps or higher panels, that's where your fully rated system is. And that will put you in a commercial industrial application. Any question about this? So that's basically where 600 amp or higher, rule of thumb, you can get 100 amp fully rated panel if you want to. For 600 amp or less, that's where the application, or higher, that becomes all the way up to 6,000 amp. Fully rated system. Any question about that, guys? Any question? So everything is rated for the main, and the feeders over computation device are rated for the same interrupting value. Take this. So what's Chris says, we said this is the rule. What you're looking at, the fully rated is a rule. Let's take the exception. Here's the exception. Look what they do, the smarter than Chad. I don't know why they didn't come up with this. Here we go. The same panel. I have 20.8 kiloamp. This is my 25 kiloamp. The 25 is the rating of the interrupting rating of the fuse, meaning after 25, all hell will break loose and that fuse will not act as it's supposed to. My interrupting rating is 20.8, so I am well within my 25K interrupting rating. Okay, let's look at that. These are the main. This is my main. Let's look at the subs. Each one of these is rated for 10K. So these are 10K. Each one of these circuit breakers are rated for 10K. But if I have a short circuit right here, I will have a 20.8K. If I have a short circuit right here, I will also have 20.8K. So the question would be, Chad, what the heck are you doing? Look at this number and this number, okay? And look at this number and this number. It doesn't take a genius to realize if I have a short circuit right at this terminal, load terminal of the fuse, this circuit breaker, will this circuit breaker be able to handle the main? Would you be able to handle this short circuit? Yep. Let's go to the subs. How about here? If I have a short circuit right here, I calculated 20.8. Anything in this panel is 20.8. If I have 20.8 here, but my circuit breaker is rated for 10, would that circuit breaker be able to handle it? No. Would that be circuit breaker will be able to handle it? No. So that's what they call it. Then they came up, the smarter than Chad came up with the series rated. Here's how the series rated works. If you have a short circuit right in this area, the fuse and this circuit breaker will act together. So the little guy will look at the current, that 20.8 thousand, look at it and say, I can't handle this. The few circuit breaker will look at it and say, I can't handle this. By design, they make him coordinate with each other. I can't handle it. So instead of trying to interrupt, what's the problem is if you try to interrupt, it will weld an arc. So if the value here is larger than number 10, that circuit breaker will basically halt, freeze, doesn't open, and wait and wait and wait and wait until Big Daddy here will take care of the problem, till the fuse ahead of it will open. That's it. That's what series rated is. You have a short circuit in any one of these branches. If the short circuit is higher than 10, only if it's higher than 10, which is, by the way, which is only 10% of the time. So you have bad news here 10% of the time, really. Most of the time, guys, most of the time, your short circuit will be where? Will be way down here, way down in where the equipment is located. And if I have a short circuit right here, 9.5K, right down on the branch circuit, which one do you think is going to wake up and trip? That guy. Why? Because it's rated for 10K, Chad, and this is within the capability of this circuit breaker. So we're taking a chance. If you have a short circuit right inside the panel on the load terminal of the circuit breaker, which is going to be very high because you're so close to the transformer, that only under these circumstances you need the main fuse to open, which is bad news because you de-energize the whole panel. And Rob is sitting there and saying, "Are you kidding me, Chad? What happened to localizing the getting rid of the branch only, the faulted branch? Series rated are not good when it comes to coordination. Only they can coordinate up to 90% of the time. So what happened to the 10%, Chad? Well, we can't live without it. What's the likelihood that an idiot will jump in here and go short right in the three-phase panel or something? Could happen. If it happens right in here, and that short circuit is high, as in Chad going there and bolting one phase to the ground or two phases together inside the panel, then you know what? If that's that high, we want to de-energize the whole panel. We don't care. Okay, so what's series rated is when you have a circuit breaker downstream with a circuit breaker fuse upstream coordinate with each other. So if the short circuit downstream is higher than the capability of the circuit breaker downstream, it will freeze, stop, doesn't move, and wait until the circuit breaker or the fuse upstream clear the fault. That's it. Who cares? Why would we even think of something like this? Because cost. So this is commonly used most likely on, I would say, 400 amps, 200 amps, 100 amp. Very common use, guys. 400 amp or lower. Sometimes 500 amp, we see 500 amp. So these are the panels that you have. You're not going to see this one on a 4,000 amp switchgear. Don't even think about it. So you're going to see, and most of the time, guys, most of the time, this is what we see, the 400 amp or lower, most of the time. Why? Because 400 amp or lower is, these panels are, most of the time, they are your lighting and receptacle panels in a commercial industrial buildings. These are your small loads, lighting and receptacle panels. Okay, so why do they do it? Cheaper pieces of equipment. The difference between a 25 kiloamp, 25 kiloamp circuit breaker and a 20 amp, 10 kiloamp circuit breaker could be 50% extra on the 25. So the price is high because they have to design the magnetic circuits differently, more robust, and so forth. So series rated, cheaper equipment used mostly on lighting circuits, lighting panels, and receptacle panels. 400 amp or less commonly used. You can get them all the way up to 500 even. Any question?
To keep them both from going on the fully rated.
Coordination on the fully rated. What's to get them to not to go? If I have a short circuit right here, what's not to get them? I have to coordinate the two fuses together. The coordination. So, and I don't want to go there. So that will be one like this. that will be circuit here and another circuit right here. So if this will be the main, this is my main, this is my, say, 20 amp. So it's right underneath it. So if there's a short circuit, which one is going to see it? Right in here. We're moving in this area, the one underneath it. If that's to freeze and not do anything, then the second, that's we do coordination. So over-computation coordination for a series rated panel, guys, is not as good as for a fully rated panel. Any question? That's it. That's what series rated. Next quarter, guys, we have an expert from Colorhammer and comes and shows a lot of more details about this. Just remember that. Okay, short circuit calculation. The last thing is, guys, how to do a short circuit calculation. Let me just do a couple of things about short circuit calculation. To find the short circuit calculation of a transformer, we're going to do this in details later on, but this is very simple calculation right here. This one is 500 kVA, and the voltage is 480, okay, volt, and the impedance is 5%. Z is the impedance. So I have the impedance is 5%, the transformer is 500 kVA, and the voltage on the secondary side is 480. Find the available short circuit out of this transformer so I can size the fuses. Very simple, very easy piece of cake. Here's what you do. You find I, you take the 500 K, divide by 480. You guys want it, let's make this one a three-phase transformer, 1.73. Everybody knows this formula. That's how you find the full load current of a transformer. Press, can you give me the answer for this, please? So 500 divide, is it 600?
It's 602.
602. So the amp on it is 602 amps. So basically find the full load current of the transformer. That's easy, right? To find the short circuit, find the full load current of a transformer. Second step, that's step number one, piece of cake. Step number two is, my friends, then you take the I short circuit, take the I, divide it by the Z, the impedance. Okay, what does that mean, Chad? Take the 602, divide this by the impedance. What's the impedance? The impedance is right here, Z, the impedance. This is what is it, 0.05. Press, please. 12,000 in. That's it. Now, who cares? The question is, why? Who cares? Take this. I want to go put a circuit breaker right here. My circuit breaker here is 600 amp. Chris, can you predict what's the interrupting rating of this circuit breaker have to be? If it's available is 12, the next standard 15. So this is going to be a 15 kilo amp circuit breaker, if they make them. That's it. Short circuit calculation will help you size the interrupting rating of the circuit breaker, right? Piece of cake. Any question, guys, about finding a full load current of a transformer? Full load current of a transformer. Take the kVA divided by the voltage and the multiplier for the three-phase, if any. Find the full load current, divide the full load current by the impedance. So if the impedance here was 10%, what do you divide here? By 0.1. If the impedance here was 0.2%, you divide 2%, not 0.2, 2%. You divide here by 0.02. Done. Who cares? That's how we size the interrupting rating of circuit breakers. The interrupting rating of circuit breakers. The more efficient, now, Chris, if you look at this, do you expect if the impedance is more efficient, meaning the impedance is low, if the transformer is more efficient, meaning the impedance is low, would you guys expect the interrupting rating to be high? That's why more efficient transformers, impedance low, short circuit is high. So you really have to find this happy medium. Short circuit is high is bad news. What does that mean? I need a higher circuit breaker interrupting rating. What does that mean to your bottom line? More money to spend. So that's kind of the catch-22 between being efficient transformer, pumping more short circuit, then you have to have higher level equipments to handle that short circuit. You have to have the happy medium. The impedance of the transformer. Everybody knows what the impedance of a transformer is. Transformers made out of windings. These windings make impedance. They smarter than Chad. They calculate this impedance in a percentage, and they give it to you as a percentage. The higher the percentage, the more impedance the transformer is, the less efficient the transformer is. Why? Because if you have high impedance here, guys, there's a lot of current that's cooking inside the transformer, doing nothing, just being eaten, digested inside this transformer. And I promise you, this is just the touching the short circuit. We'll get into that one, guys, in details. Okay, any question, guys, about the short circuit? Take the full load of the transformer, divided by the impedance, piece of cake. Okay. Panel boards and load centers. If you guys want to think ahead, I know you probably don't want to do that, but we have a PowerPoint presentation YouTube done by Cutler Hammer. Todd Christensen, one of the experts in panels and switchgear, switchboards, and load centers. He did a great presentation last year. It's on YouTube about the difference between load centers, panel boards, switch gears, switchboards, and so forth. I want to tell you one thing, because we're residential, we will open this can of worm as we move in commercial, because that's where they are. If you're residential, you're doing load center. As far as the code concerned, as far as the NEC code concerned, they're all panel boards. As far as the industry concerned, a load center, guys, load center is usually 100 amp, 60 amp, 100 amp, 200 amp, maybe 300 amp, maybe. These are called load centers. They make them cheaper, they make them smaller in size, smaller in depth, so they can fit in a 2x4 stud. So it's a cheaper, easier, most economical way of making panel boards. So they can fit in a 2x4. What does that mean to you guys? And I mentioned, take this. If this is 100 amp, if it's 100 amp load center, if it's 100 amp load center, then you probably will have all this. Look at that. This base you can fill. If it's 100 amp load center, you can fill it with this base. Can be filled with all circuit breakers. These are circuit breakers and so forth. If it's a load center, the black is load center. If it's load center, take this. If that was a panel, look what they do. They take this. I'm going to use a different color. They take a smaller space to fill it with circuit breakers. So the question with what happened to the rest? Why do you think they allow bigger gutters? This is called the gutters. So they allow a bigger gutter around the circuit breaker, so you can maneuver all your circuits in a three-phase and commercial industrial. So long story short, guys, if you have a 100 amp panel, the 100 amp panel load center might look that wide, right? If the same 100 amp load center, it will look wider, deeper, taller, or longer. Bigger equipment. Why? Because they want to allow the people to maneuver the circuit breaker, the conductors, more room for you to pull the conductors through the gutters on the panel. That's all we're going to say. So cheaper. Why do we have load centers? Cheaper equipment. Most of the time, 100 to 200 amp, 100 amp, and 200 amp panels. You use them in residential all the time. Fits by two in a stud, between stud in a 2x4. You go to a next level is panel boards. They're bigger, deeper. You name it. More gutter space, you can pull your conductors. Can I use a load center in a commercial building? Yeah, no problem. 200 amp, no problem. What's the problem is if it's an engineered project, they don't allow you that. They want a panel board. When they say a panel board's big, you have to buy a panel board. Now take this. The difference between 200 amp panel board and 200 amp load center could be 50% more expensive. So substantially expensive. The material is big, large, more robust. So when you think load centers, think residential, very light commercial. When you think panel boards, think commercial and industrial. Does that make sense? The project that you guys are doing, this is called load centers. All the stuff that you size with Chad, there are load centers. That's it in terms of load centers. The last thing, selective coordination and non-selective coordination, guys. I'm going to show this 100 amp panel and this 20 amp going all the way to my garbage disposal. So if I have a short circuit, back to my friend Nick, that he just shorted the short circuit right here, Chad. I did a short circuit right to the garbage disposal. Which one should trip first? have short circuit in the garbage disposal. Which one should trip first from this panel? The 20 amp, right? That 20 amp circuit breaker have to trip first. That's what we call a selective coordination. Non-selective coordination is when the 100 amp trip every time the garbage disposal have a problem. That's non-selective. Now, I hope you agree with me that a non-selective is bad for you, right? And selective is great because it localizes, sectionalizes the faulted part of your system. A short circuit right in here in this light right now, go short it. It should take down the branch circuit that feeds this. It shouldn't take the switch gear down and done with it. You would hope so. That's why we do a ground fault. That's why we do the over current protection coordination, which you, my friends, will be doing with your friend Chad in the industrial project for sure. Any question about coordination, selective coordination? The circuit breaker closer to the fault or the short circuit will trip first to minimize the disturbance in the system, right? If you're in an auto building and every time you have a short circuit in the panel and the whole building goes dark, I bet you will be cursing and giving a lot of fingers to a lot of people who design it and install it, right? So that's what selective overcapacity coordination. You guys will be doing a study with us here. And it's required by the code Ashley only on emergency systems. If you have an emergency system, it's required by code to do overcapacity coordination. Recommended for everything else, but required on emergency systems. That's what I have, guys. I have one little thing I'm going to show you, and then okay, let's go here. Okay, we talked about these, right? The stages. We talked about the panels all the way. The fuses, different type of fuses, cartridge fuses, current limiting fuses. I didn't talk about the current limiting fuses, guys, but later on we'll talk about current limiting fuses. It's really simple. If you have a 50,000 amp coming into the fuse, out of the fuse, you will have 20 amp coming out. That's what a current, it limits the current that goes through. Limits the current that goes through. And we will talk in the commercial more about the current limiting fuses. Current one-time fuse, non-current limiting, one-time different fuse circuit breakers. I want to bring to your attention, guys, the interrupting rating at the face of a circuit breaker. This is 10,000 amp, rated for 12240. Can't use it higher than that. The same thing if you look at 10,000 amp. Chris, if you look at the information right here on this circuit breaker, it will tell you if you are to use this circuit breaker as a switch, like Chad is going to be doing, to switch fluorescent lights. I hope we didn't switch anything. If you're using it as a switch, oops, there you go. We switched the second. That's what I was trying to avoid. Yeah, if you if you're using it as a switch, then it has to be rated as a switch, and you see SWD on it as rated for a switch. As rated for a switch. That's the only circuit breaker that I was trying to avoid at a headset. Okay, so that's a circuit breaker, and you guys can look at these. The circuit breaker. We talked about the parallel series, the series rated circuits. Series rated could be a fuse with a fuse, or circuit breaker with circuit breaker, or a fuse with circuit breaker. Doesn't matter. Okay, and I want you, my friends, to the last thing I want you guys to look at is page 632. 632, please. 632. 632 have page 632 have some comparison between fuses and circuit breakers, comparison of panel board type. If you use a panel board as a service entrance equipment, does it have to be listed as a service entrance equipment? Yes. If you use, that's what it tells you over here. If this panel is 100 amp, can I protect it with an overcapacity device that's 200 amp? Are you kidding me, Chad? No. If it's a 100 amp panel, the cover, the bus inside is 100 amp, I can't protect it more than 100 amp. I can put 90 amps, 80 amps, 60 amps, but I can't protect it for less than 100, more than 100. Okay, so that's what they're telling you guys. Here's my stuff. Okay, so if they're rated must have a short circuit current rating. All these must have a short. If you guys read on the side, they're telling you this is fuse fully rated, fuse main, fuse breaker series rated, breaker main, breaker fully rated, and breaker main, breaker branch series rated. And it tells you about the series rating and the fully rating for all of them. So let me see here. Okay, so if you guys must be listed or marked suitable for service. Yep, all of them have to be listed for service if you're using service. Must have a short circuit current rating for the available current. Yep, all of them have to have a short circuit capable of being interrupted. Must be marked with its short circuit rating. Do I have to mark them that this panel is 50 kVA, 50 kiloamp? Yes, you have to be marked them. Must be marked with series rated. Only the panel. Oh, by the way, if this panel is series rated, which, oh, by the way, it is. This one is a series rated panel. If you must have a label here that says series rated panel somewhere here. Find it. Look for it. So if it's a series rated panel, you have to have a label that says series rated panel. And if you look at that, and it says caution combination system rated for this amount, identify replacement is required. So it has to tell you rated for, say, so combination system rated for, let's say, 2500 amps or so. Identify replacement components required. So what they want you to do, guys, is when you go change the circuit breaker in a series rated, you have to use the same circuit breaker that the manufacturer are recommended in this circuit to maintain the integrity of the series rating of that panel. So you can't just plug any fuse in any panel. If it's series rated panel, you have to use the same type, the same size, the same interrupting rating of the same manufacturer of that particular fuse if it's series rated panel. Otherwise, they wouldn't acknowledge it. It might not work. Because remember, these two are working together, coordinated in the factory. They make them, they test them as an assembly, a whole system. Must have an interrupting rating. Branch circuit must have an interrupting rating for available short current line side. So if you can see if it's all of them, they have to have interrupting unless it's rated for series rated, so they can depend on the main to interrupt them. Main fuse are current limiting. If you guys look at this one right here, this is a current limiting fuse. Must be sized determined by the service. Yep, you have to size them based on the service or the panel. Time characteristic curve. You have to use the time current characteristic curve for all the manufacturers. Yep. So current limiting. They say about current limiting here, guys. For the current limiting, let me just draw one little thing, and then Chad will stop here. If I have 600 amp and this interrupting rating 65 kiloamp, the available short circuit coming in here, let's just say 60,000 amp, coming out here, it will knock it down from 60 to 40,000 amp. That's called current limiting fuse. That's where the concept of current limiting fuse is. Can you guys see that? Specially designed fuse, where as the current goes right through the fuse, it alters the chemical and the structural characteristics of the material, and it acts like a choke. It chokes the current and stops it. So look at this, a 60,000 amp at the line side of the fuse, when it comes on the, just goes right through the fuse. This is, by the way, a fuse. When it goes right through the fuse will choke it and only allow 65 kiloamp. Only allow 40 kiloamp. Who cares? Then everything else here can be rated for 40,000 amp. They allow you guys to use, by choking the current, they allow you to use the cheaper equipment rated for a lower interrupting rating on the line, on the load side of the fuse. We'll talk about that current limiting, guys, in the commercial industrial, but this is just a FYI. Any question, guys? Any question? That's it. I will remind you guys that NEC, as we all know, 240.6 in Article 240.6 give you from 15 amp all the way to 6,000 amp rating. 6,000 amp. Non-adjustable, right? 240.6. A is non-adjustable. B is adjustable. If you go to B, it's adjustable circuit breaker, so you can adjust them. If you have an adjustable electronic circuit breaker, I can tweak it to give you 943.5 amps, and that's okay. So how many sizes can I get for adjustable? Unlimited. If your circuit breaker is adjustable, you can get unlimited amount of sizes. If it's fixed, non-adjustable, then you're going to go to 240.6A, and I will give you all the sizes of the circuit breaker and the fuses. That's it. That's all I have. Any question, guys? Any question, my friends? I think we have, that's basically what we have.